So about the pendulum, the beam of light bouncing between the mirrors, you can use that to build a very accurate clock. Einstein then imagined what that same clock would look like if it were moving relative to us. So here's what we'll do, Jim. We'll carry the clock while moving along the stage, keep the clock moving, dim the lights, and now we'll watch from our perspective. We are stationary with the stage. Jim is moving relative to us. That little box you can see is Jim's head, camera. In Jim's view, because he's at rest with his clock, the light simply bounces straight up and down between the mirrors. But look at our view. We've added a trail so you can see it clearly from where we're sitting. The light doesn't go straight up and down. As Jim carries the clock along, the beam traces a zigzag path, diagonal up then diagonal down, so across the stage it looks triangular. Let me sketch that. These are the mirrors in Jim's light clock. In Jim's frame, the light takes the short vertical path. In our frame, watching the moving clock, the light takes the longer slanted path between the same mirrors. Now here's Einstein's key point. The speed of light is the same for everyone. If the light covers a longer path for us, while moving at the same speed, each tick must take longer in our view. That's why the moving clock runs slow. Moving clocks run slowly. That isn't a trick, it's real. Time genuinely passes at a different rate for Jim than for you watching him. Our time is personal to us. There is no single absolute time. We don't notice this in everyday life because Jim's speed here is tiny compared to the speed of light, so the effect is minuscule. But imagine we sent Jim off in a rocket, would you like that, and accelerated him to about 94% of the speed of light. He flies outward for 5 years, by his own watch turns around and flies back for another 5 years. For Jim, the trip takes 10 years. For us, because his moving clock runs slow, about 29 years pass on Earth. Jim would return in 2042, having aged only 10 years. That's real testable physics time travel to the future. Right, so we've earned the headline, time travel into the future is not science fiction. It's a routine feature of the universe. Once you've seen the light clock thought experiment the way we just did with Jim, the rest follows with a kind of quiet inevitability. If everyone agrees that light's speed is the same, and if the path is longer for the moving clock than for the clock at rest, then the moving clock must tick more slowly. That's not a magician's flourish. It's geometry in space-time wearing a very sensible suit. But let's clear up the question that always arrives next. Slow relative to what? With. Because there's a subtlety here that Einstein was very precise about. From Jim's point of view, while he glides along with his light clock, he is the one who's stationary. His clock looks perfectly normal. It's ours back in the seats that appears to run slow. That symmetry isn't a bug. It's the very heart of relativity. What breaks the tie in any real trip with a going out and a coming back is the story of the journey, not a single snapshot of motion. Turnarounds and accelerations matter because they change the path you take through space-time. Two people can start together and reunite later, having experienced different amounts of time, not because one life really ran slower in an absolute sense, but because their world lines, their routes through the fabric of space and time were different. The universe keeps meticulous accounts. There's a neat way to say this. Without a single equation, every traveller carries their own clock, and that clock tallies proper time, the time along their path. Move quickly for a while, swing around, move quickly back, and your path is different from your friend who stayed at home. When you meet again, the books don't match. One of you has fewer ticks in the ledger. That difference is not philosophical. We've measured it with the most exact timepieces humans can build. Let's move from stage props to laboratories and the sky above us. There's a charming, almost mischievous experiment you can do with nature's own timing devices, muons. They're born in showers high in the atmosphere when cosmic rays strike air nuclei. A muon at rest decays on average after a tiny fraction of a second, so brief that if you did the arithmetic with no relativistic effects, almost none of them should survive the dash to sea level. Yet we detect floods of them at the ground. Why? Because to us, watching them hurtle toward Earth at speeds close to light, their moving clocks run slow. Their internal countdown is stretched, giving them time to arrive. Turn the picture around, and from the muon's perspective, its clock is perfectly normal. Instead, the atmosphere ahead is length, contracted so the distance to the ground is shorter. Two descriptions, one set of observations, all reconciled by the same underlying geometry. If you prefer your demonstrations with polished metal rather than cosmic rain, consider the now classic flights of atomic clocks. Take matched exquisitely stable clocks, leave one in a lab and send the other on a long journey in an aircraft. Bring them back together and compare. You'll find a sliver of disagreement exactly where Einstein tells you it should be. The same corrections keep your sat-nav honest. The clocks aboard navigation satellites tick in a different gravitational environment and at high orbital speeds. If we ignored relativity, the timing errors would accumulate by tens of microseconds each day, enough to misplace you by kilometers. Engineers don't ignore relativity. They build it into the system so your phone can hail a taxi to the right street corner. Notice I slipped in a new ingredient there, gravity. Up to now, we've been playing with motion alone, special relativity. Einstein's later leap, general relativity, says something even more startling and more beautiful. Gravity isn't a force tugging at you from afar. It's the way mass and energy curve space-time, telling clocks how to tick and paths how to bend. A clock deep in a gravitational well on the surface of the Earth, for example, ticks more slowly than a clock higher up out of the well. Place one atomic clock on a mountain and another in a basement, they will not agree. Lift one to orbit. It speeds up for the gravitational reason, but slows down because it's moving swiftly. In low Earth orbit, the motion effect wins. Astronauts come home younger by a few milliseconds than their twins on the ground. It's small, but it's there written into the data. All of this equips us to be quite precise about the future travel story we told with Jim's hypothetical rocket. If he cruises at a substantial fraction of the speed of light, his gamma factor, the little bookkeeping number that falls out of the geometry, might be around 3. That means 1 year for Jim could correspond to 3 for us watching from home. Send him away for 5 of his years, turn him around and bring him back after 5 more. He steps out having lived 10 years. We've gone on for roughly 30. That's the physicist's version of a fairy tale, with no magic and no dragons, only the rules of the universe enforced with quiet consistency. But hang on, someone always says if motion is relative, wasn't the Earth rushing away from Jim as much as Jim was rushing from Earth? Yes, along the straight segments of the trip there's symmetry. The asymmetry arrives because Jim changes direction. He feels the push of engines. The homebound friend doesn't. Those non-uniform bits of the journey, the accelerations mark the paths as different. If you like pictures, draw 2 routes on a map. One is a straight line across a city. The other is a scenic detour with hairpin turns and switchbacks that rejoins at the same destination. Both start and finish together, but one is simply longer. In space-time, length is measured in a way that blends space and time so that the scenic route yields less proper time. Experiments done on fast-moving particles in circular accelerators confirm this daily. Their lifetimes stretch precisely as predicted, and when we force them through bends with magnets, the bookkeeping still balances. It's worth pausing here to absorb the philosophical tremor Einstein set off. There is no such thing as absolute time. That sentence can sound like poetry or provocation, but it's really a gentle reminder to be honest about what the world shows us. Time is what clocks measure, and when good clocks disagree in repeatable, predictable ways depending on their motion and their place in a gravitational field, it's our job to generalize our notion of time, so these facts fit comfortably. That generalization isn't a mess, it's incredibly elegant. The same equations that tell you a moving clock runs slow tell you how starlight arcs around the sun, how black holes cast shadows, how the universe expands. The pieces lock together. Now, if future-ward travel is almost humdrum, what about the audacious direction that stories love the past? Here the universe becomes cagey. General relativity contains exotic solutions, mathematical worlds, where you can in principle loop back on yourself along a closed time-like curve. There are fanciful machines like infinitely long rotating cylinders, speculative cosmic strings, and the more alluring idea of a wormhole, a tunnel stitching 2 regions of space-time together. If you could hold a wormhole open, and that if hides an entire forest of difficulties, and if you moved one mouth about in a relativistic way, the clocks at the 2 ends could fall out of step. Walk through, and you might emerge at a time earlier than you entered. It's a delicious idea, but before we fit a wormhole with velvet ropes and a ticket kiosk note, the price of admission you'd need exotic matter with negative energy density to prop it open. And where we've looked seriously in the disciplined mathematics of quantum, fields we find stringent limits that make constructing a human-sized portal look unpromising. There's also the nagging suspicion voiced with characteristic dry wit, as the chronology protection conjecture that the universe may simply forbid macroscopic time machines by triggering violent instabilities the moment you try to assemble. 1. For now then, the honest verdict is forward time travel is easy, you're doing it now, and you can do it faster by moving fast, or by sitting in a strong gravitational field. Backward time travel remains at best speculative, and at worst inconsistent once all the physics is properly tallied. That doesn't mean we lock away our curiosity. It means we take the hint that reality gives us, pursue ideas, test them where you can, and be disciplined about where wonder stops and wishful thinking begins. Before we leave the stage, Let me cement the everydayness of future travel with a few more tangible pictures. Imagine two identical, exquisitely crafted wristwatches beating with the same tiny heartbeat. You stay at home. Your friend spends a year aboard a jet doing nothing more dramatic than circling the globe. You meet again, and the watches disagree by a whisper nanoseconds or microseconds depending on the path. It's small, but it accumulates so much so that the global network of timekeeping institutions must continuously compare and correct. The world's clocks are not merely synchronized, they're relativistically negotiated. Or think of deep space probes that have been voyaging for decades. Their onboard oscillators drift, but we account for the relativistic stretching and squeezing of time along their trajectories when we decode their radio whispers. Our conversation with the far reaches of the solar system is phrased in relativistic grammar. There's a final image I love because it blends the poetry with the precision. Picture space-time as a vast four-dimensional landscape, a terrain with valleys carved by gravity and ridges shaped by motion. Each of us is a walker tracing a path across it, our heartbeat, the metronome counting the steps. Some paths scramble across steep slopes, some wander gently through meadows. When two walkers meet at a gate and compare step counts, they needn't match. Neither cheated, they simply took different routes in a world where routes matter. And the rules that set the shape of the land are the same rules that let us predict eclipses to the second map the cosmos, and design the technologies that have woven themselves into our ordinary lives. So yes, time travel to the future is possible, measured, and if you're wearing the right watch, visible. And because we are an inquisitive species, we'll keep pressing on the more speculative door marked past, not to break the universe, but to understand it better. Next, if you like, we can step closer to gravity's deepest wells near neutron stars and black holes, where time's malleability becomes dramatic enough to feel mythic, yet remains stubbornly and beautifully the work of physics. Right, let's step closer to the places where time's flexibility stops feeling like a footnote and starts to feel like weather. Gravity's deepest wells, neutron stars and black holes are not just heavy, they reshape the pace at which seconds pass. If the light clock with Jim made the idea plausible, these objects make it visceral. Start with a neutron star. Imagine, if you like, a sun's worth of mass squeezed into a sphere the size of a city 12 kilometers across, give or take. The surface gravity is extraordinary, but what matters for our story is what that gravity does to time. If you could hover safely a few meters above such a surface, never mind for a moment the engineering, your watch would run noticeably slow compared with a friend's identical watch far from the star. How slow? For a fairly typical neutron star, about 1.5 times the sun's mass and roughly 12 kilometers in radius, the slowdown is on the order of 20%. That is when a friend far away experiences 1 minute your clock near the star might tick off only 48 seconds. This isn't a trick of language, it's a measurable, calculable effect from the same geometry that bends starlight and steers planets. It's worth picturing this carefully. Think of time as a river. On Earth, the flow is almost uniform from town to town. You never notice much difference. Near a neutron star, the river runs thick and slow. You look at your wristwatch and it seems perfectly ordinary. Tick, tick, tick. But when you reunite with your friend who stayed well upstream, their watch has piled up more ticks than yours. You didn't dawdle. You simply walked for a while along a bank where the current is sluggish. In the ledger of the universe, you've logged fewer seconds. You don't have to travel to such extremes to see gravity's influence. Climb a mountain on Earth with a portable atomic clock, and there's a whisper of a difference. Higher up, you are a little farther out of Earth's gravity well, so your clock runs ever so slightly faster. At 2,000 meters above sea level, the gain is about 20 billionths of a second per day. It's invisible to us, but not to our instruments. Over a year, that tiny advantage builds to several millionths of a second. Modern timekeeping centers actually share and correct for these differences, so that the world's clocks are in a literal sense negotiated across gravity. The satellites that guide you to the right cafe rely on the same discipline. Their clocks, free-falling high above us, sit in a weaker gravitational field than the clocks on the ground, so they tick faster for that reason. But they're also racing along and motion slows them. The two effects don't cancel, they add with a sign. At typical navigation satellite heights, gravity's boost is larger than motion's break, so the onboard clocks gain roughly a few dozen millionths of a second each day relative to ours. Engineers pre-correct this, so that when the signals fall to Earth, your phone's arithmetic puts you on the correct pavement rather than a block away. If relativity were a mere philosophical flourish, sat-nav would be a whimsical art. It isn't. It's a utility precisely because we treat time as the physical quantity it is. Now, black holes. The phrase has acquired a slightly melodramatic life of its own, but the physics is clean. Take enough mass, squeeze it into a small enough volume, and the curvature of space-time becomes so intense that not even light can find a path out. The boundary we call the event horizon is not a material surface, it's a one-way gate in the geometry. If you linger far away and watch a friend fall towards that boundary, you'll see their signals slow, redden and fade. To your eyes, the patient observer at a safe distance, their time appears to stretch and then almost freeze as they approach the edge. This is where the imagination can snag. It's tempting to say they stop at the horizon. They don't. That's an artifact of your vantage point. In their own experience, the only one that counts for their heartbeat and their thoughts, they cross the horizon in a finite time and carry on. The river of time in their patch of space-time does not end. It simply runs in a direction that can never return to you. There's a detail I think is helpful here because it counters the picture of inevitable tearing and doom at the horizon. It depends on the size of the black hole. For a black hole 10 times the sun's mass, the sort made in a stellar collapse, the tidal forces near the horizon are ferocious. The difference in gravity between your head and your feet would be catastrophic. For a supermassive black hole, the kind that anchors a galaxy's center, the horizon is vast, millions of kilometers across, and the tidal gradients right at the edge can be gentle enough that you might float through without immediate drama. That doesn't mean you can come back. The geometry remains a one-way street. But the idea that you would be ripped apart at the doorstep is not universally true. It depends on the mass. Even before we reach a horizon, time can slow dramatically near one of these giants. Picture a spacecraft on a safe orbit skimming near the edge of a supermassive hole. The crew can go round for an hour by their own clock and return to find that much more time has passed for colleagues waiting far away. In that sense, black holes are perhaps the most efficient future time machines. Nature offers no fairy rings, just gravity doing what gravity does. The cost, of course, is risk. Get your trajectory wrong and the future you time travel into will be inside. You might wonder how we know this isn't just an elegant story. One answer is that we've now watched clocks in strong gravity behave just as the equations predict. Stars orbiting the black hole at the center of our galaxy are a prime example. They loop in tight, fast ellipses, and when one dives in, close the light from it, arrives redder and later than it would without relativity's corrections. In other words, the star's clock as seen by us during that close pass runs slow. Instruments on large telescopes have traced this dance for years, and the data sit comfortably in general relativity's embrace. There's another effect, more subtle but equally visualizable, called the Shapiro delay. Imagine a light signal grazing a massive object on its way to us. Because the terrain of space-time is curved, the straightest path is longer in time than it would be in flat space. The signal arrives tardy by a small, predictable amount. Radio astronomers have measured this when signals skirt the sundial. It's as if the valley of gravity doesn't just slow local clocks, it makes the journey itself take longer even for light. It's a lovely confirmation that we're dealing with one consistent landscape rather than a bag of separate tricks. If we return to Earth for a moment, because everyday numbers help, the International Space Station provides a neat composite picture. The astronauts orbit at a few hundred kilometers up, traveling at roughly 7.5 kilometers per second. Their speed slows their time, their altitude speeds it. In that balance, the motion wins. They age a touch less than their friends on the ground milliseconds over the course of a long mission. Not enough to excuse a birthday party, but enough that in a strict sense, they've skimmed the future. For listeners who like a concrete, almost tactile sense of scale, here's a trio of time scales you can hold in your head on a mountain. 2 kilometers high, a good atomic clock gains about 20 nanoseconds per day relative to a twin at sea level. That's 20 billionths of a second, small yet measurable. On a navigation satellite, a comparable clock would gain on the order of 40 or so microseconds per day due to gravity and lose a few microseconds due to motion. Engineers fold the net effect tens of microseconds into the system so your Maps app keeps its promises. Near the surface of a typical neutron star, a clock can run 20% slow relative to far away. Spend an hour there again, pretend you have a miraculous hovercraft and your friend's hour and a quarter have flowed past elsewhere. Those numbers are not decoration, they're the quiet fingerprints of a single idea. Time is part of the geometry, not a universal drumbeat. There is a natural question that follows, and it's one I find both practical and slightly poetic. Can we use gravity deliberately to harvest more future? The answer in principle is yes. If you lived your life orbiting near a very massive object, safely say a supermassive black hole at a respectful distance, you could engineer a difference. To you, a year would still feel like a year. To friends who stayed in gentler fields and slower orbits, more than a year would pass. You would be a traveller to their future. In practice, of course, the engineering is forbidding. Radiation environments near accretion disks are punishing, and the fuel costs for holding orbits that are close yet safe are vast. But nature doesn't ask us to do it, it merely permits it. And sometimes the permission slip is enough to satisfy a curious mind. If we're content for now to keep our feet on the ground and our imagination in the sky, the moral remains clear. The universe doesn't hand us a single absolute now. It offers a landscape of nows, stitched together by the paths we take. Move fast, dip into gravity's valleys, climb out. Each choice writes a different tally in the book your heart carries. Next, I suggest we visit the edge cases where our current understanding is stretched but not broken, places where quantum mechanics and curved space-time meet. There even the idea of a clock becomes delicate, and time itself starts to show the grain of a deeper structure. But before we get there, keep the mental picture steady. Seconds are not universal coins. They're local leaves on a tree whose branches twist through space and curve under weight. Once you see that tree, the strange becomes clear, and the clear becomes rather wonderful. Right, let's step closer to the places where time's flexibility stops feeling like a footnote and starts to feel like weather. Gravity's deepest wells, neutron stars and black holes are not just heavy, they reshape the pace at which seconds pass. If the light clock with Jim made the idea plausible, these objects make it visceral. Start with a neutron star. Imagine, if you like, a sun's worth of mass, squeezed into a sphere the size of a city 12 kilometers across, give or take. The surface gravity is extraordinary, but what matters for our story is what that gravity does to time. If you could hover safely a few meters above such a surface, never mind for a moment the engineering your watch would run noticeably slow, compared with a friend's identical watch far from the star. How slow? For a fairly typical neutron star, about 1.5 times the sun's mass and roughly 12 kilometers in radius, the slowdown is on the order of 20%. That is when a friend far away experiences 1 minute your clock near the star might tick off only 48 seconds. This isn't a trick of language, it's a measurable, calculable effect from the same geometry that bends starlight and steers planets. It's worth picturing this carefully. Think of time as a river. On Earth, the flow is almost uniform from town to town. You never notice much difference. Near a neutron star, the river runs thick and slow. You look at your wristwatch, and it seems perfectly ordinary. Tick, tick, tick. But when you reunite with your friend who stayed well upstream, their watch has piled up more ticks than yours. You didn't dawdle. You simply walked for a while along a bank where the current is sluggish. In the ledger of the universe, you've logged fewer seconds. You don't have to travel to such extremes to see gravity's influence. Climb a mountain on Earth with a portable atomic clock and there's a whisper of a difference. Higher up, you are a little farther out of Earth's gravity well, so your clock runs ever so slightly faster. At 2,000 meters above sea level, the gain is about 20 billionths of a second per day. It's invisible to us, but not to our instruments. Over a year, that tiny advantage builds to several millionths of a second. Modern timekeeping centers actually share and correct for these differences so that the world's clocks are in a literal sense negotiated across gravity. The satellites that guide you to the right cafe rely on the same discipline. Their clocks free-falling high above us sit in a weaker gravitational field than the clocks on the ground, so they tick faster for that reason. But they're also racing along and motion slows them. The two effects don't cancel, they add with a sign. At typical navigation satellite heights, gravity's boost is larger than motion's break, so the onboard clocks gain roughly a few dozen millionths of a second each day relative to ours. Engineers pre-correct this so that when the signals fall to Earth, your phone's arithmetic puts you on the correct pavement rather than a block away. If relativity were a mere philosophical flourish, sat-nav would be a whimsical art. It isn't. It's a utility precisely because we treat time as the physical quantity it is. Now, black holes. The phrase has acquired a slightly melodramatic life of its own, but the physics is clean. Take enough mass, squeeze it into a small enough volume, and the curvature of space-time becomes so intense that not even light can find a path out. The boundary we call the event horizon is not a material surface. It's a one-way gate in the geometry. If you linger far away and watch a friend fall towards that boundary, you'll see their signals slow, redden, and fade. To your eyes, the patient observer at a safe distance, their time appears to stretch and then almost freeze as they approach the edge. This is where the imagination can snag. It's tempting to say they stop at the horizon. They don't. That's an artifact of your vantage point. In their own experience, the only one that counts for their heartbeat and their thoughts, they cross the horizon in a finite time and carry on. The river of time in their patch of space-time does not end. It simply runs in a direction that can never return to you. There's a detail I think is helpful here because it counters the picture of inevitable tearing and doom at the horizon. It depends on the size of the black hole. For a black hole 10 times the sun's mass, the sort made in a stellar collapse, the tidal forces near the horizon are ferocious. The difference in gravity between your head and your feet would be catastrophic. For a supermassive black hole, the kind that anchors a galaxy's center, the horizon is vast, millions of kilometers across, and the tidal gradients right at the edge can be gentle enough that you might float through without immediate drama. That doesn't mean you can come back. The geometry remains a one-way street, but the idea that you would be ripped apart at the doorstep is not universally true. It depends on the mass. Even before we reach a horizon, time can slow dramatically near one of these giants. Picture a spacecraft on a safe orbit, skimming near the edge of a supermassive hole. The crew can go round for an hour by their own clock and return to find that much more time has passed for colleagues waiting far away. In that sense, black holes are perhaps the most efficient future time machines. Nature offers no fairy rings, just gravity doing what gravity does. The cost, of course, is risk. Get your trajectory wrong, and the future you time travel into will be inside. You might wonder how we know this isn't just an elegant story. One answer is that we've now watched clocks in strong gravity behave just as the equations predict. Stars orbiting the black hole at the center of our galaxy are a prime example. They loop in tight, fast ellipses, and when one dives in close, the light from it arrives redder and later than it would without relativity's corrections. In other words, the star's clock, as seen by us during that close pass, runs slow. Instruments on large telescopes have traced this dance for years, and the data sit comfortably in general relativity's embrace. There's another effect, more subtle but equally visualizable, called the Shapiro delay. Imagine a light signal grazing a massive object on its way to us. Because the terrain of space-time is curved, the straightest path is longer in time than it would be in flat space. The signal arrives tardy by a small predictable amount. Radio astronomers have measured this when signals skirt the sunday. It's as if the valley of gravity doesn't just slow local clocks. It makes the journey itself take longer, even for light. It's a lovely confirmation that we're dealing with one consistent landscape rather than a bag of separate tricks. If we return to Earth for a moment, because everyday numbers help, the International Space Station provides a neat composite picture. The astronauts orbit at a few hundred kilometers up, traveling at roughly 7.5 kilometers per second. Their speed slows their time, their altitude speeds it. In that balance, the motion wins. They age a touch less than their friends on the ground, milliseconds over the course of a long mission. Not enough to excuse a birthday party, but enough that in a strict sense they've skimmed the future. For listeners who like a concrete, almost tactile sense of scale, here's a trio of timescales you can hold in your head. On a mountain 2 kilometers high, a good atomic clock gains about 20 nanoseconds per day relative to a twin at sea level. That's 20 billionths of a second, small yet measurable. On a navigation satellite, a comparable clock would gain on the order of 40 or so microseconds per day due to gravity and lose a few microseconds due to motion. Engineers fold the net effect tens of microseconds into the system so your Maps app keeps its promises. Near the surface of a typical neutron star, a clock can run 20% slow relative to far away. Spend an hour there again, pretend you have a miraculous hovercraft and your friend's hour and a quarter have flowed past elsewhere. Those numbers are not decoration, they're the quiet fingerprints of a single idea. Time is part of the geometry, not a universal drumbeat. There is a natural question that follows, and it's one I find both practical and slightly poetic. Can we use gravity deliberately to harvest more future? The answer in principle is yes. If you lived your life orbiting near a very massive object, safely say a supermassive black hole at a respectful distance, you could engineer a difference. To you, a year would still feel like a year. To friends who stayed in gentler fields and slower orbits, more than a year would pass. You would be a traveler to their future. In practice, of course, the engineering is forbidding. Radiation environments near accretion disks are punishing, and the fuel costs for holding orbits that are close yet safe are vast. But nature doesn't ask us to do it, it merely permits it. And sometimes the permission slip is enough to satisfy a curious mind. If we're content for now to keep our feet on the ground and our imagination in the sky, the moral remains clear. The universe doesn't hand us a single absolute now. It offers a landscape of nows stitched together by the paths we take. Move fast, dip into gravity's valleys, climb out. Each choice writes a different tally in the book your heart carries. Next, I suggest we visit the edge cases where our current understanding is stretched, but not broken places where quantum mechanics and curved space-time meet. There even the idea of a clock becomes delicate, and time itself starts to show the grain of a deeper structure. But before we get there, keep the mental picture steady. Seconds are not universal coins. They're local leaves on a tree whose branches twist through space and curve under weight. Once you see that tree, the strange becomes clear, and the clear becomes rather wonderful. Right, this is the place where two great ideas start talking to each other across a narrow bridge. On one side, relativity, which treats time as part of the geometry and lets gravity and motion shape its flow. On the other, quantum mechanics, which tells us the world has a grain, a shimmer, a fundamental restlessness. If you try to build a clock that is both exquisitely small and impossibly precise, quantum mechanics leans over your shoulder and says gently but firmly, "Not like that. Begin with a simple picture." A clock in the most generous sense is anything that repeats an atom's electron cloud, oscillating between two well-defined energy levels, a crystal resonator humming a pulse of light ricocheting between mirrors. To read time, you need two things: a steady rhythm and a way to count its beats without disturbing the rhythm. The difficulty at bottom is that the act of measurement is never perfectly gentle. The smaller the system, the more your very act of peaking jiggles it. This is the spirit of the time, energy, uncertainty relation. It doesn't say that energy is fuzzy in quite the same way position and momentum are. Time in standard quantum theory isn't an operator you can probe like position. It says that if a process lasts only a very short duration, the energy you can associate with it is correspondingly indeterminate. Push time resolution down and you invite energy spread up. Now mixing gravity. A clock has mass, or at least energy, and energy gravitates. Concentrate it into a tiny region, and you deepen the very gravitational well that slows your clock. If you kept compressing and boosting precision without limit, you would eventually make the region so dense that it forms a black hole. The clock disappears behind a horizon. You've lost the very thing you tried to perfect. This hand-wavy argument, made crisp by various authors over the years, hints at a limit to how sharply time can be sliced when quantum jitter and gravitational back reaction are both present. It's a signpost pointing toward a deeper theory, quantum gravity, where space-time itself may have an elemental texture like the weave of a very fine fabric. You don't need to chase such extremes to see quantum influence on timekeeping. Consider modern atomic clocks, the best our species has built. They use light tied to an atomic transition as their pendulum. These devices are so stable that if you ran one for the age of the Earth, it would lose or gain less than a second, an absurd statement that's nevertheless true in spirit. With this stability, you can do a charming trick: lift the clock by a small height and watch it speed up because of the change in gravitational potential. On Earth, a shift of tens of centimeters is enough for the effect to appear. If that feels almost comically sensitive, that's the point. Time is not a monolithic drumbeat. It's a field quantity like temperature that you can map from place to place. In a very literal sense, with sufficiently good clocks, you can do chronometric geodesy. You can measure height and gravitational potential by how fast local seconds flow. There's an image I like for these quantum limited clocks. Imagine balancing a coin on its edge and flicking it just enough to make it precess so it rocks back and forth at a regular rate. If you flick too hard, it falls, too softly, and the signal is too faint to read. You're always negotiating between precision and stability. Quantum mechanics sets those negotiations at the smallest scales. Relativity dictates the prices paid in different gravitational neighborhoods. The meeting point is not a conflict, it's a partnership. All of this talk of clocks and rhythms invites a more profound question. What is it that's flowing? Relativity encourages us to think of the world as a four-dimensional map with time simply another coordinate, special, yes, but woven into the same fabric. In that picture, the universe looks a little like a library with every event already shelved, the block universe. The flow we feel is then a feature of how brains like ours made of moving thermally agitated matter process information along their world lines. Whether you like that framing is partly a matter of temperament. Physics itself doesn't need an extra something moving through the map. It needs laws that tell you which paths are possible and how clocks tally along them. But there is an arrow, a direction that matters, and you can feel it when you look at steam swirling from a kettle or a glass shattering but never unshattering. That arrow isn't etched into the geometry, it's written into the statistics of matter. Entropy, which you can think of as the number of microscopic ways to arrange the stuff of the world while leaving the overall look unchanged, tends to grow. Given a choice between a few delicate arrangements and a vast number of messy ones, the messy ones win by sheer weight of numbers. The past of our universe appears special because it was astonishingly low in entropy at the beginning, smooth, simple, with matter and radiation evenly spread, the gravitational field quietly poised. From that simple opening chord, complexity blooms and disorder rises, and systems like us can remember the past, but not the future. Our memories, our strategies, our very notion of cause and effect ride on that asymmetry. This is where relativity and thermodynamics clasp hands near black holes. Black holes have entropy, and a prodigious amount of it at that. Their surface area, in the sense of the area of the event horizon, acts like a measure of how many internal microstates are hidden from us beyond the gate. This leads to the famous story that black holes have temperature and radiate faintly if the universe could isolate them long enough. The details of that faint radiation come from quantum fields living on curved space-time, and while the full tale wanders into deep theoretical woods, the take-home fact is clear and vivid. Gravity, quantum mechanics, thermodynamics, information aren't separate fiefdoms, they are chapters of one book. If you heat a piece of metal, you don't expect its weight to change your recipe. But at the horizon of a black hole, temperature, time, and geometry trade lines in the same play. Let's make that tangible with a thought photograph. Picture yourself orbiting safely near a supermassive black hole in a sturdy craft with good shielding. Out the window you see the background stars distorted into arcs and rings, a lens made not of glass but of curved space. Your onboard clock hums content. Far away a colleague watches your signal. They see the rhythm of your pulses stretch and slow as gravity deepens around you. To them you seem to be dancing in treacle. To you nothing peculiar happens. Your seconds feel the same because that's what feeling a second means. After an hour by your count, you fire the engines and climb out. You rendezvous with your colleague and compare watches. Their ledger shows more ticks. You haven't cheated the universe, you've obeyed it. The future for you arrived with a slightly thicker stack of pages turned for them. It's often helpful to step back to everyday scales so the brain has two anchors, the fantastical and the familiar. Consider the path of a morning. You wake, you boil water, you walk into sunlight. Photons that left the sun 8 minutes earlier warm your face. The light that left Jupiter, perhaps an hour ago, would in principle show you a storm still raging from last week's telescope images. Even without moving fast or finding gravity's valleys, you are surrounded by pockets of the past delivered by light at finite speed. If you walk across a field with a friend, chat lag is negligible. If your friend is on Mars, you both need patience by necessity. The speed of light, far from being an inconvenience, is the friend that makes causality clean. It gives the universe structure, a cone around every event, delimiting what can influence what and when. Those light cones are the rails that keep paradox at bay in the worlds we actually inhabit. Paradox is a tempting word when you turn to the old chestnuts about going backwards. What if I prevent my own grandparents from meeting? The neat minimalist reply, if closed time-like curves were in play, is called the Novikov principle, the P2. Only consistent histories are the ones that occur. That sounds tautological because it is. It rescues logic by forbidding choices that would contradict themselves. Whether nature ever permits circumstances where such logic is required is another matter. Every time we examine plausible mechanisms for pastward travel carefully, they demand either exotic conditions we've never seen and don't know how to create, or they sprout instabilities that likely snuff them out. It's not a proof that the past is unreachable. It's a strong hint that the future, facing arrow we live with, is not a trivial local convention, but a global property of the universe's story. We can, however, play richly within the forward arrow. Particle accelerators routinely extend the lifetimes of unstable particles with speed. Astronauts collect tiny age discounts in orbit. Deep mines host clocks that lag by a whisper. Navigation satellites preemptively trim their heartbeats so our maps snap to pavements. Mountaintop observatories literally live in faster time than valley towns below. A volcano of romance has erupted around these facts in popular culture, but the facts themselves are perfectly sober. Time travel to the future is a set of knobs. You can turn speed, height, gravitational depth, and the result is as real as jet lag, just ordinarily much smaller. There's another image to carry with you because it gathers the whole story like a spiral shell. Imagine a vast railway network. Every traveller carries a watch and the tracks are laid across hills and valleys. In lowlands, weak gravity trains run a little faster. Up steep gradients, strong gravity, they slow. Some lines are straight inertial paths. Some take scenic curves, accelerations. When travelers meet at a junction and compare watches, they rarely match exactly, and that mismatch isn't a scandal. It's the signature of the journey. Space-time is that railway. Your world line is your ticket. The stamps on it, the seconds you accrue, depend on where you went and how you got there. Now, since you asked for pictures that help the mind's eye hold these three in a tidy row: a light cone, a narrow torch beam from an event spreading outward. Everything inside the cone can be touched by what happened. Everything outside cannot. That's causality, simple, austere, and deeply comforting. A river in gentle country, it runs smooth and quick. In marshy banks and rocky narrows, it drags. Clocks are little boats. Each boat's oar strokes feel steady. Compare logs later and you'll see the differences. That's relativity's time dilation. A library, the shelves already hold the chapters. The way you read them page by page in a forward order, with memories and expectations, is set by entropy, by the shape of probability, in a world that began simple and is busy becoming intricate. That's the arrow. From here, if your curiosity enjoys a steeper climb, we can look at two frontiers that sit just beyond the comfortable porch light. The first is the early universe, where the arrow of time was minted. Why was the beginning so extraordinarily low in entropy? And how does cosmic expansion relate to that? The second is the quantum gravity scene, where the very idea of before and after may be encoded in something more primitive than time itself. Perhaps correlations between subsystems, perhaps an emergent parameter that behaves like time only when many degrees of freedom conspire. But we needn't hurry. The best thing about the subject is that it's hospitable. You can sit with the modest exact facts. Moving clocks run slow. Gravity slows clocks. Light speed is the same for everyone. Causality is shaped like a cone, and already the universe becomes richer, more legible. You can add black holes and neutron stars and the faint rain of muons, and the picture gains grandeur without losing its footing. And you can let philosophy peer in from the doorway, block universes and arrows and the meaning of now without letting it steal the scene. The scene, after all, is already beautiful, a cosmos in which your path matters, where the seconds you collect are your own, and where the future is a landscape you can, within limits and with imagination, choose how to enter. Right, let's give the idea of time as landscape a larger canvas and draw the lines so you can see exactly where you could walk. There are three pieces I want to place side by side, so the picture feels inevitable rather than mystical. First, how to read a map of time without equations. Second, how the universe itself gives us a kind of communal clock. And third, why the arrow points the way it does so, memory, and cause feel aligned with physics rather than superstition. Begin with the map. Imagine a sheet of graph paper stretched across the stage. Left-right is the distance along the floor, up-down is the passage of time. Now sketch two dots. Meet at the foyer before the show, and meet again by the exit after the show. Draw different paths between them. One path is a straight diagonal line, that's the person who sat mostly still strolling out at the end. Another path snakes about, that's the person who jogged around the block, popped to the mezzanine, then rushed back. Here is the quietly surprising rule of relativity in space-time. The straight path between two fixed events maximizes the proper time, the tick count on your wrist. The scenic route with accelerations reduces your proper time. This is the twin story in a picture. The traveler who departs and returns with accelerations has a zigzag in their world line, and therefore fewer heartbeats to show for it. No paradox, no magic, just geometry that treats time and space as partners. If you prefer a hands-on version, try this mental experiment. Take two identical metronomes, their tick is your stand-in for a perfect clock. Leave one on the stage. Send a volunteer with the other to the far end of a very long, smooth, moving walkway, then bring them back. When they reunite, click both metronomes together and listen. In ordinary life, the mismatch is too small for ears, fractions of microseconds, but the sign of the mismatch is certain. The metronome that took the scenic route has tallied fewer ticks. Laboratories have repeated this logic at speed with atomic clocks on aircraft and satellites. The numbers are small, but stack up with relentless ledger-like honesty. And pleasingly, the same bookkeeping explains why unstable particles live longer when we whip them around a collider, and why our astronauts are younger by a whisker when they come home. Now widen the lens. If everything is relative, people ask, is there any shared sense of now in the universe? There isn't an absolute one. Einstein closed that door gently but firmly. But there is a remarkably natural cosmic one. The young universe was a hot, nearly uniform plasma glowing with light. As it expanded and cooled, it became transparent, and the glow slipped free. We still bathe in the afterlight, the cosmic microwave background, a faint radio hush that fills all of space with an almost perfect temperature, of about 2.7 Kelvin. If you coast with the average flow of galaxies neither rushing toward nor away from that glow, you are by definition at rest in the cosmic frame. The time kept by such coasting observers is called cosmic time. It is not superior or compulsory, it is simply convenient, because on very large scales, it lines up our watches across the cosmos. In that sense, when cosmologists say the universe is about 13 and a bit billion years old, they mean that's the proper time measured by observers who ride with the general expansion since the hot beginning. This cosmic clock also gifts you an image you can hold. Step outside on a crisp night and look up. Every star is a message from the past, because light takes time to travel. The moon is a little over a second away, the sun is 8 minutes away. The brighter galaxies are millions of years in the past. Delicate red smudges in modern telescope images show us light that set off more than 10 billion years ago, when the universe itself was young. We are surrounded by a museum with no closing hours, its exhibits arranged by distance and look-back time. Telescopes are not just magnifying glasses, they are time machines that respect causality to the letter. No loops, no paradoxes, just a patient queue of photons delivering the history of everything. Now about the arrow, the reason teacups break and never unbreak, and why you can remember breakfast but not dinner from tomorrow. The geometry we've been discussing doesn't by itself contain a preferred direction. The equations of general relativity work as willingly if you flip the sign of time. The arrow arises from initial conditions and statistics. The universe began in an extraordinarily simple, smooth state, low entropy. Entropy here is just a count of how many microscopic arrangements fit the same macroscopic look. Smoothness is special because gravity loves to amplify lumps. Start very smooth, and as the cosmos expands, little wrinkles grow into galaxies and stars and chemistry and life, and the rich, messy structures we know. Start in a scrambled high entropy state, and there's nothing for time to do. The arrow of time is in this story, the statement that the past boundary condition was special. Physicists sometimes call this the past hypothesis. It's not a cheap trick, it's a clean way to encode a real fact about our world. The early universe wore a remarkably tidy suit. You can feel the consequences in your own kitchen. When you boil water, energy flows from hot to cold, and the molecular jostling available to the system increases. When you drop milk into coffee, the swirling pattern spreads complexity through the cup. You never see the reverse without cheating, because the set of micro-configurations that make unmixed coffee with milk droplet on top is tiny compared with the number that make even tan. Entropy's rise is a statement of odds in a world that began stacked to favor simple states initially. And black holes sit at the extreme end of that logic for a given mass. Nothing can hide more internal micro-configurations than a black hole. That's why their horizon area behaves like entropy, why their temperature is inversely related to size in those famous formulae, and why their growth in classical processes is one way in area, an echo of the second law. Let's make the black hole story crisp enough to picture without a single algebraic symbol. You and a friend float safely far from a supermassive black hole. You've each got a lamp that flashes once per second by your own clock. You dive closer on a stable circular path. Your friend stays put. As you skim the edge, your friend sees your flashes arrive more and more slowly and at longer, redder wavelengths. To them, your time seems to slog. You, looking out, see the opposite. Their signals are blue-shifted, seeming to arrive faster. When you climb back and compare watches, their ledger has accrued more seconds. That is gravitational time dilation measured as a real effect, not an optical illusion. Astronomers have watched stars at our galaxy's center do this very dance. As one modestly named S2 sweeps near Pericenter, every 16 years or so, its spectrum shifts just as predicted by relativity. Its clock, as seen by us, then runs slow. The cosmos keeps its books. If the apparent freezing at a horizon still bothers your intuition, a last image helps. Think of a waterfall shrouded in mist. From the cliff top railing, the safe distance, you watch a leaf drift near the lip and then vanish into the spray. The closer it gets to the edge, the more the mist scatters and reddens the light from it, so its signals grow faint and delayed. From your vantage, the leaf's last clear wave takes ages to reach your eye. But down in the water, the river flows smoothly over the brink in finite time. Both descriptions are true in their own frames. The leaf's clock doesn't stop. Your view of the leaf's clock slows to a halt. The event horizon is that kind of boundary in space-time, a gate that makes returning a signal to you impossible after crossing not a brick wall that halts the traveller's heartbeat at the threshold. Let's come back to Earth, literally, to tie these grand pictures to experiences you can imagine doing. If you set 2 precision clocks on a lab bench and then lift one by 30 centimeters, about a foot, The higher one will tick faster by a few parts in 10 to the 16 each second. After a day, the difference is tens of nanoseconds, billionths of a second. Modern optical lattice clocks can see that difference. This is not speculative. If you take a matched pair of clocks, leave one in a basement and put the other on a mountain, 2 kilometers up the mountaintop, clock gains about 20 nanoseconds per day. If you place a clock on a satellite, two clean effects tug in opposite directions. Gravity lets it tick faster, being farther from Earth's mass, while its high orbital speed slows it. The net result for navigation satellites is a gain of roughly a few dozen microseconds per day relative to ground clocks. Engineers design the onboard frequency so that once in orbit, the wrong tick rate becomes the right one as viewed from Earth. That pre-correction is why your mapping app drops a pin on exactly the cafe door rather than in the river. Here is a home experiment you can do with imagination alone, but that captures the essence. Picture two towns in a valley and on a plateau. Each noon they exchange a pulse of light marked with the exact time the pulse left. Because light takes a finite time to travel, and because clocks in the stronger field tick more slowly, the records each town keeps will show a systematically different rhythm, even if both towns are utterly honest. A century ago, this would have been philosophy. Today, it's the standard operating procedure of a civilization that relies on synchronized time to run power grids, financial markets, and global communications. We live inside relativity's corrections. They are part of our plumbing. What about the idea of grandfather paradoxes and password trips? We've already set the sober expectation nothing in the physics we use to navigate the world needs loops in time. The universe's causal structure is laid out by light cones. Every event has a cone of influence, spreading forward what it can affect, and a cone from the past what could have affected it. Stay inside those cones and cause and effect is clean. Exotic solutions that bend those cones around to meet themselves require conditions, negative energy densities, sustained on large scales or extreme cosmic structures we have no evidence for, and good theoretical reasons to doubt. Nature seems to have a talent for allowing the idea in equations while erecting 1,000 practical keep-out signs in reality. I think it's fair to say that's a kindness. It lets our stories be adventurous without letting logic collapse. To close this stretch, I want to give you 3 mental postcards that glue the chapter together. The Minkowski postcard, a straight world line between 2 meetings, gives the most proper time. Add Kink's accelerations and you come back younger. That's the twin story reduced to a diagram you could draw on a napkin. The cosmic postcard, the microwave background, is the universe's gently humming reference frame. Coast with it, and your watch reads cosmic time. A practical shared clock that lets us say meaningful things like galaxies grew from tiny seeds over billions of years, and have those years mean the same to everyone coasting. The arrow postcard entropy grows because the beginning was special. The rise in disorder powers memory engines and the entire cascade from hydrogen to humans. Black holes sit at the far end of that story with horizons whose area behaves like the book's index of hidden possibilities. From here, the next step, if you're game, is to reach for the seam where quantum theory and gravity overlap in experiments. Not just thought experiments with impossibly small clocks, but real laboratory proposals putting ever heavier objects into quantum superposition and asking whether gravity responds. Measuring gravitational time dilation over centimeters done, and then millimeters, listening for the way gravitational waves modulate time across the arms of our detectors. Each of these tightens the weave of the fabric we've been describing, turning a beautiful picture into an even more precise one. And each, I think, leaves you with the same quietly joyful conclusion: time in our universe is local, path-dependent, and gloriously consistent, strange only until you learn how to read the map. Picture the stage again. The light clock is set, 2 mirrors facing each other, a beam ricocheting between them like a heartbeat. Jim shoulders the clock and strolls across the floor. From his point of view, nothing peculiar happens. The beam goes straight up and straight down. From ours, the beam must cross a diagonal, tracing a longer route, while still moving at the same universal speed. Longer path, same speedslottig. That is the entire story of special relativity in a single gesture. Moving clocks run slow, not as a trick of optics, but as geometry made visible. Hold that picture while we widen the world around it. Time is not a drumbeat dictating the same rhythm everywhere. It's more like a river whose current changes from place to place. On Earth, we barely notice the eddies because our speeds are small and our gravitational well is modest. But nature keeps meticulous accounts, and if you bring the right instruments, the ledgers never lie. You can see it in the cold rain of muons from the sky. These subatomic particles are born high in the atmosphere and decay so quickly that without relativity, few should ever reach the ground. Yet detectors at sea level register them in abundance. In our frame, they're sprinting close to light speed, their internal clocks slowed, so their short lives stretch long enough to arrive. In their own frame, their clocks are ordinary, but the air below is length contracted, so the finish line is nearer. Two descriptions, one set of facts bound by the same geometry. You can also see it in polished metal. Fly an atomic clock around the world and compare it to a twin left in a laboratory. The travelling clock disagrees by a whisper. Satellites carry clocks too, and we rely on them so casually that it's easy to forget the audacity involved. Far above Earth, those clocks tick faster because gravity is weaker, but they also tick slower because their orbits are swift. The net result, about plus 45 microseconds per day from gravity and misty 7 microseconds from motion, for roughly plus 38 microseconds overall, is built into the system, so your mapping app takes you to the cafe door rather than the riverbank. If relativity were philosophy, GPS would be folklore. Instead, it's plumbing. The corrections are in the pipes. Now add gravity properly. Einstein's later leap was to say that gravity isn't a force tugging at you from a distance. It's the way mass and energy curve space-time. Clocks deep in a gravity well run slow. Put one on a mountain and another in a basement, and the high clock pulls ahead by tens of nanoseconds per day. Lift the high clock into orbit, and now two effects compete. Gravity lets it race, speed reins it in. On the International Space Station, the speed wins and astronauts come home younger by a few milliseconds over long missions. Not enough to skip a birthday, but enough to prove the rule. If you want drama, step nearer to the truly heavy things. A neutron star is a sun's mass squeezed into a city-sized sphere. Hover just above the surface, never mind how, and your time slows by nearly 20% relative to a friend floating far away. Spend an hour there, and your friend lives through roughly 75 minutes. That same geometry steers starlight shapes orbits and gives galaxies their graceful curves. It's one story told with many voices. Black holes press the point to its limit. The event horizon is not a wall, but a one-way gate in space-time. Watch a colleague dive toward it, and their signals stretch, redden, and fade. From your safe distance, their clock seems to slow toward a halt. In their own experience, nothing singular happens at the edge, particularly for a supermassive black hole where the tides at the horizon can be gentle. They cross in finite time and carry on. The river of their seconds flows smoothly into a region that cannot send messages back. Two valid views from two different paths sewn together by one geometry. All of this is easiest to hold if you learn to read a space-time map without equations. Place two meet-here dots on your mental graph before and after, and draw possible routes between them. The straight world line with no accelerations accumulates the most proper time that Traveller's Watch shows the largest number of ticks. Add a kink turnaround accelerate, and you shorten the tally. That is the twin story sketched on a napkin, no paradox required. The asymmetry isn't about who really moved, it's about who felt the push of a turn. Accelerations mark the world line, and the accounting follows them. Is there any shared now? Not an absolute one, but the universe gifts us a practical, communal clock. The cosmic microwave background, the faint afterglow from when the hot, early plasma became transparent, bathes all of space at about 2.7 kelvins. Drift with the average flow of galaxies so that this glow looks the same in every direction, and your watch measures cosmic time. When cosmologists say the universe is about 8 billion years old, they mean this proper time, along those coasting world lines since the hot beginning. It's not superior, it's convenient, like setting your wristwatch to a city's time so your friends' appointments make sense. While the geometry tells you how clocks tally, it stays silent on the question of direction. The equations work equally well if you flip time's sign. The arrow we all feel the reason teacups shatter and don't reassemble comes from statistics and initial conditions. Entropy, the count of microscopic arrangements that fit a macroscopic look, tends to grow because there are simply more messy arrangements than tidy ones. Our cosmos began in an astonishingly smooth, low entropy state. From that simple opening, gravity grew, structure, chemistry blossomed, and memory became possible. We remember breakfast, but not dinner from tomorrow, because the past boundary was special. This past hypothesis isn't hand-waving. It's a clean way to encode what observations tell us. The early universe wore a tidy suit, and from that tidiness springs an arrow. Black holes sit at the far end of that arrow. Their horizon area behaves like entropy, an index of hidden microstates we can't see. They even have temperature, and in principle radiate faintly. Quantum fields, living on curved space-time, insist upon it. The details are subtle, but the message is clear. Gravity, quantum mechanics, thermodynamics, and information are chapters of the same book. Heat a piece of metal, and you don't expect the sun to bend its path. Yet, near a horizon, temperature, time, and geometry, hold a quiet conversation and agree on the bill. Causality holds the plot together. Every event sits inside a light cone that marks what it can influence and what can influence it. So long as world lines stay inside those cones, cause and effect are clean. Exotic solutions that try to fold those cones back onto themselves, closed time-like curves require conditions we've never seen. Infinitely long spinning cylinders, cosmic strings of immense tension or wormholes propped open by negative energy on macroscopic scales. The mathematics entertains them. The physics we can test offers 1,000 reasons to doubt they're available to engineers. It may be that the universe protects its chronology and informal conjecture with a formal backbone try to build a time machine and quantum fields rebel. The quantum conversation arrives even when you don't ask for drama. Try to make a clock both tiny and arbitrarily precise, and quantum mechanics leans over your shoulder. Short timescales invite large energy spreads. Confining energy invites gravity. Push too far, and you curve space-time enough to hide your clock behind a horizon. In that hand sketch lives a hint of a deeper limit. Perhaps there's a finest grain of when a scale where the concepts of before and after have to be rebuilt from correlations rather than ticks. We are not there yet, but the signposts are visible. None of this needs to float above life. You can feel the structure in a morning walk. Sunlight on your face left the photosphere 8 minutes ago. The moon's light is a little over a second old. Jupiter's storms, if you could see them with the naked eye, would be an hour in the past. Even standing still, you're already a traveler through a museum of delayed messages. Send a radio hello to Mars tonight and wait. The reply cannot cheat the cone. Our impatience is tamed by a constant we didn't choose, and in return we receive a universe with clean causality. If you want 3 images to carry away, make them these: a river whose current changes with depth and speed. Your little boat, your clock rose steadily, but when you reunite with friends who chose different channels, the logbooks don't match. No one cheated, the currents differed. A railway map drawn across hills and valleys. Straight tracks across the plain yield the longest travel time on your watch. Switchbacks through the hills cost you seconds. Meet again at the junction, and the mismatch is the signature of your route. A library with every chapter shelved. The flow you feel while reading is in you in the way memory accumulates as entropy rises, yet the shelving plan still matters. Begin with a simple preface, and the story can grow. Start in disorder, and there's nothing to read. So is time travel possible? You are doing it now, at 1 second per second. You can do it faster by moving fast, or by lingering in gravity's valleys. Sail near a supermassive black hole on a safe orbit, and return with fewer heartbeats on your wrist than your friends have tallied in your absence. Fly for a year at a substantial fraction of light speed, and decades can pass at home. These are not fables. They are engineering challenges whose answers are cost, risk, and fuel, not metaphysics. Backward travel remains for the moment a tale the equations whisper, but the world refuses to stage. Perhaps that's a kindness. It leaves us with a universe where choices have consequence, memories grow in one direction, and wonder is earned honestly. The picture when you stand back is both sobering and generous. Time as local causality is clean, and the seconds you gather depend on the route you take. If you ever find yourself under a clear night sky, try this: pick a star and give it a quiet greeting. The answer you receive 8 minutes, an hour, a million years delayed will arrive when it can and not before. In that patient exchange is everything we've talked about: light's constancy, the shape of space-time, the arrow and your place in it. And when you check your watch on the walk home, remember that it's not just keeping time. It's telling the story of your path through a universe that makes room for many stories, all consistent, all personal, all stitched to the same law. Consider how delicately a ripple in space-time announces itself. A pair of black holes merge in a distant galaxy, and for a heartbeat they ring like struck bells. That ringing is not sound, but a periodic stretching and squeezing of space and time themselves, gravitational waves. On Earth, the L-shaped halls of laser interferometers listen for those ripples. When a wave passes, one arm becomes imperceptibly longer, while the other becomes shorter, trading places with each oscillation. The size of the effect is astonishingly small, fractions of a proton's width over kilometers, but the pattern is unmistakable. A rising chirp as the holes spiral together, then a fading ring down as the new larger hole settles. You can think of these observatories as timekeeping instruments, so precise they can hear the universe flex its seconds. A gravitational wave doesn't just tug on rulers, it modulates the beat of clocks along its path. For an instant, different parts of the detector live through slightly different amounts of time, and the lasers add those differences up into a measurable song. The idea that waves in gravity carry timing information helps with a broader picture. Time is not merely what clocks display, it is part of the terrain. Mountains, strong gravity slow you. Open plains, weak gravity let you stride. Rivers, high speed, force you to angle your boat. Still bays, rest, give you the longest drift between the same two piers. Once that map is in your head, famous thought experiments become scenes you can stage. Picture a long train gliding past a platform at steady speed. Two lightning bolts strike the front and back of the train, hitting the rails at what the person on the platform calls the same moment. For the passenger at the train's midpoint, the flash from the front must fight against the train's motion, while the flash from the back has the train rushing toward it. The back flash arrives first. Simultaneous has slipped its absolute mask. Each frame carries its own sensible account. No paradox, only the honest accounting of light's finite speed and the geometry that keeps its pace constant for everyone. Because light's speed is fixed, and the map is four-dimensional, intervals in spacetime behave differently from distances in ordinary space. The straight world line between two reunions gives you the most proper time. Add detours, accelerations, and you come back with fewer ticks on your watch. That single sentence underwrites everything from the twin story to the way particle beams live longer when whipped round circular accelerators. You can feel the same logic in orbital freefall, a satellite coasting along a geodesic. The straightest possible path in curved space-time experiences no engine push and maximizes its local sense of doing nothing. Its clock tallies time according to altitude and speed alone. That's why the corrections for navigation satellites are steady and predictable. We know their paths, so we know their time. Sometimes it helps to pin down the numbers so imagination has footholds. Fly a fast spaceship at 94% of light speed, and your Lorentz factor the little geometric multiplier that tells you how much your time differs from someone at rest sits around 3. 1 hour for you is roughly 3 hours for your friend at home. Push to 99% and the factor climbs to about 7. 99.9% raises it to more than 20. The arithmetic is relentless. As you approach light speed, each extra 9 buys you a disproportionate leap in time dilation, but each extra 9 costs vast amounts of energy. There is no cheat code that gets around the fuel and engineering. Future travel is a budget problem, not a logical one. Gravity offers you another way to adjust the ledger. Imagine a vast supermassive black hole with a calm environment, no raging accretion disk, no deadly particle hell. The closer you orbit while staying on a stable, safe track, the slower your clock runs relative to someone waiting in interstellar space. On orbits just a few gravitational radii from the horizon, a single hour for you could correspond to many hours far away. Astronomers have watched hot clumps of gas near our own galaxy's central black hole circle in tens of minutes. That gives you a physical sense of scale. If a craft could skim those same paths safely, the cruise time would be thickened by gravity, while the universe outside turned its pages more quickly. The price is navigation drift inward by mistake and you won't send postcards home. All this talk of clocks and maps invites a natural question. Is there anything like a shared clock for the cosmos? There is a practical candidate. The universe, when young, was a hot, nearly uniform plasma that glowed like a perfect furnace. When it cooled enough for atoms to form, the glow streamed freely. We still live inside it, the cosmic microwave background, a bath of light at just under 3 Kelvin. If you drift with a great river of galaxies so that this afterglow looks the same in every direction, your watch measures what cosmologists call cosmic time. On that communal schedule, the universe has aged a little short of 14 billion years. It isn't an absolute ruler imposed on all. It's a convenient one that aligns the stories told by distant observers. You and an astronomer halfway across the visible universe, each coasting with your local galaxies, can agree on how much time has flowed since the glow was set free. While the geometry sets the rules, it does not dictate why time feels like it flows from earlier to later, why memories pile up behind you and possibilities unfold ahead. That arrow emerges from statistics and beginnings. Entropy, the number of microscopic ways to arrange the world without changing its coarse appearance, tends to grow because there are vastly more messy arrangements than tidy ones. Our universe began in an astoundingly smooth, low-entropy state, and gravity, left to its own devices, amplifies wrinkles into galaxies, stars, and planets. From smoothness, complexity blooms. From complexity, gradients arise. From gradients, engines and life can do work. You can watch that logic in your cup as milk swirls into coffee. The delicately arranged droplet has few microstates. The tan mixture has countless. The second law is not a scold, it's a census. Black holes sit at the far end of that census. For a given mass, nothing hides more internal arrangements than a black hole. Its event horizons area plays the role of entropy. Push two holes together and the total area never goes down. An echo of entropy increases written in geometry. Stranger still, when quantum fields are allowed to speak, a black hole has a temperature and can radiate very faintly. That slow leak is negligible for big holes, but the concept matters. Temperature, information, and time meet at the horizon and shake hands. The deep puzzles that live there, how information is accounted for, are part of the frontier where we expect quantum theory and gravity to reveal a common language. Closer to home, quantum mechanics already limits how finely we can slice time with a physical clock. Shorten the timescale you want to resolve, and the energy involved in your tick grows uncertain. Pack that energy into a small region, and gravity answers. Push hard enough, and you would curve space-time so much that your clock hides behind a horizon. In that crude sketch is a suggestive message. There may be a flaw under, when a scale where ticks are replaced by correlations and time becomes an emergent summary of change in larger systems. We don't possess that full theory yet. What we do have are exquisite experiments that push both sides of the bridge. Atomic clocks now measure gravitational time dilation over centimeters. Metrologists dream of mapping geopotential height by clock readings alone. Physicists put ever heavier objects into delicate quantum states and ask whether gravity treats those superpositions like single things or many. Each result tightens the net that future theory will have to fit. Because you ask for pictures that help the mind collect a few, you can return to the lighthouse beam. A gravitational wave passes and the lighthouse sweep speeds imperceptibly up and down across the rocks. That speeding up and down is the wave's effect on time. The light's constant pace turns that timing into a measurable shift in the interference fringes miles away. The valley towns. Two towns trade noon signals every day, one in a valley, one on a plateau. Both are honest. Over months, their logs disagree by tiny, predictable amounts because noon in the valley is a shade slower. Build accurate enough clocks and you could draw a contour map of the landscape using nothing but time. The river lock. A spacecraft drops into a deep gravitational lock coast for a while, then rises back to the main channel. The captain's log shows fewer ticks than the sister ship that stayed upstream. No engines can pay back those ticks. They were never taken by a thief. They were simply written differently because of the route. Let's ground the grand with a few concrete safe figures. Lift a superb optical clock by 30 centimeters, and it will tick faster by roughly a part in 10 to the 16. That's tens of nanoseconds per day, tiny to us, plain as noon to the clock. Put a similar device on a satellite, and if left uncorrected, it would gain on the order of tens of microseconds per day relative to ground clocks, because gravity is weaker up there, partially offset by a smaller slowdown from orbital. Speed. Engineers warp the onboard frequency on the ground so that once the satellite is in its proper orbit, the clock, as seen from Earth, keeps perfect time. That single-act pre-bending timekeeping to fit curved space-time is why your rideshare arrives at the correct curb. Now return to the human story, because this is ultimately where these abstractions live, in choices, journeys and reunions. Suppose a future pilot leaves Earth on a high-gamma cruise, say 9/10, and more of light speed. They travel for a year by their own clock flip and return in another year. 2 years pass for the pilot, several for their family at home. They will come back a time traveler, welcomed by familiar faces that are a little older than their own mirror. The barriers are engineering, biology and will. Gravity offers similar bargains. Linger carefully near a gargantuan black hole with no violent disk, and your ledger of seconds will thicken more slowly than your friends. Both schemes are awkward to stage, but the principle is settled. The universe permits these differences because it is consistent about how it adds up paths. Meanwhile, the past remains, to the best of our working knowledge, a one-way gallery. You can look at it by waiting for light to arrive. You can infer it with fossils, spectra and echoes. You can fold equations that evolve states forward and reconstruct what must have been. But you cannot step into yesterday and shake hands with it. The mathematics admits fanciful corridors under conditions we don't know how to arrange. The physics of fields and stability seems to lock those doors. That's not a defeat. It's the reason memory is meaningful and promises matter. If you find yourself outside under a dark sky, try a small experiment in imagination. Choose 2 stars. Whisper to the nearer one and remind yourself that your words turned into radio would take years to arrive. Turn to the dimmer, more distant one and realize that the glow on your retina left when dinosaurs were young or when the first flowers learned to open. You are already threaded through time. You have always been. The question is not whether you travel, but how you steer. Speed and gravity are the knobs the universe gives you. Causality is the guardrail. Entropy sets the direction of the road. And your watch, the humble second counter on your wrist or in your phone, is the little compass that, if you learn to read it, tells you exactly where you are on the map. Imagine standing on a hill at dusk with a pocket watch and a good pair of binoculars. Over the ridge, a train glides by at steady speed. Two lightning forks strike the rails, one at the front of the train, one at the back. From your hilltop vantage, the flashes look simultaneous. But picture a passenger seated at the train's midpoint. The flash from the front must chase the moving carriage. The flash from the rear is racing toward it. The rear flash lands first. Two honest observers, two sensible stories, one world. Simultaneity is not a universal decree. It's stitched to your state of motion. That single scene is enough to loosen the grip of absolute time and prepare your imagination for everything that follows. Now trade the hill for a laboratory tower. At the top, a source emits gamma-ray photons. At the bottom, a detector waits. Gravity pulls on everything that carries energy, and light carries energy, so the photons lose a whisper of energy as they fall. Their frequency drops by a tiny predictable amount, the gravitational redshift. This was measured famously with the Pound-Rebka experiment on a Harvard tower in the 1950s, and it has been refined ever since with lasers and atomic clocks. You can feel the idea in your bones once you see it. If light's rhythm changes with height, then clocks, physical processes, must tick at different rates at different gravitational potentials. Time is part of the terrain. Precision timekeeping turns that poetry into plumbing. Lift a state-of-the-art optical clock by 30 centimeters and it ticks faster by about 1 part in 10 to the 16 tens of nanoseconds per day. Leave one clock in a basement and another in a mountaintop lab, and over months the difference accumulates into something you can read in an afternoon of careful comparison. The world's timing institutions exchange these slivers of disagreement constantly. They correct them. They make power grids phase, lock financial trade settle, and satellites agree. Modern civilization functions because we take seriously the fact that a second is local. If you prefer sky to wires, consider supernovae in distant galaxies, white-hot thermonuclear beacons that brighten and fade with a characteristic timetable. The farther the galaxy, the greater the redshift, and the greater the time dilation of the light curve you record. To telescopes on Earth, the rise and fall of a supernova at redshift, one ticks about twice as slowly as a nearby twin. That isn't a foggy metaphor. It's a direct visual stretching of time due to cosmic expansion, the same 1 plus Z factor that reddens the light, stretching the durations themselves. In this way, the universe hands us a communal clock face. The farther you look, the more slowly distant dramas play out to your eyes. There's a complementary communal clock humming all around us, the cosmic microwave background. It is the light last scattered, when the hot early plasma cooled enough to become transparent, and it fills space with a temperature of roughly 2.7 Kelvin. If you drift so that this glow looks the same in every direction you are coasting with the average flow of galaxies, your watch then measures cosmic time, a convenient yardstick we use to say the universe is about 13.8 billion years old. That number is a proper time for those particular world lines. Not a royal decree for all observers, but it lets astronomers across the sky line up their histories. Step closer to gravity's wells and the imagination has more to hold. A neutron star, with a mass around 1.5 times that of our Sun, squeezed into a sphere a dozen kilometers across, slows clocks near its surface by on the order of 20% relative to clocks far away. That means an hour for a hovering observer. There might be 48 minutes to a friend in deep space. That same curvature steers starlight into arcs, twangs, pulsar beams with exquisite regularity and makes orbits precess in ways that match the equations term for term. Nothing mystical is required. The geometry is precise, the numbers small or large as the setting demands, and the experiments increasingly abundant. Black holes put a clean edge on the story. The event horizon is a one-way boundary, a surface from which future-directed light rays cannot escape. Hover safely far away and a colleague's signals deepen in red and grow spaced out as they approach the horizon. From your vantage, their clock appears to slow. In their own frame, especially if the hole is supermassive and the tidal forces at the horizon are gentle, the crossing is uneventful. They fall through in finite time by their own watch and cannot return messages. Two views both correct within their domains, glued by a single unambiguous geometry. If your intuition stalls at the apparent freezing, try a waterfall shrouded in mist from the cliff. A leaf's last glints take longer and longer to reach your eye. In the water's frame, the river flows over the brink in seconds. Add motion back into the mix, and the knobs become visible. Fly at 94% of light speed, and your Lorentz factor sits around 3. Your hour is roughly 3 hours for a friend at home. Push to 99%, and the factor swells to about 7. Add another 9, and it climbs past 20. Those extra 9s are expensive. The energy required grows dramatically as you creep toward light speed, and biology shielding and fuel costs crowd in before philosophy does. Future travel by speed is a budget and engineering question. The logic is settled, the ledger is unforgiving. Gravity offers a different knob. Imagine a calm, supermassive black hole with little in the way of churning plasma, a quiet anchor at a galaxy's center. On safe circular orbits, only a few gravitational radii from the horizon, you could experience substantial time dilation. Circle for an hour by your clock and colleagues far away might chalk up several. We've seen hot gas clumps near our own galaxy's central hole complete such orbits in tens of minutes. Their light reddens and lags exactly as the geometry prescribes. A spacecraft skimming the same tracks would pay in radiation risk and navigational precision, but the principle is nature's own gravity bends space and time together. Bend time enough, and you have a respectable one-way ticket into someone else's future. Not every question about time is about dilation, of course. There is the deeper current why time seems to flow, and why it flows toward the future rather than the past. The dynamical laws that govern fundamental particles are mostly indifferent to flipping the sign of time. The arrow we feel emerges from statistics and a special beginning. Entropy, a measure of how many microscopic arrangements correspond to a given macroscopic look, tends to grow because there are vastly more disordered arrangements than ordered ones. Start the universe in an astonishingly smooth, low-entropy state. The observational verdict on the early cosmos and gravity does the rest. Tiny wrinkles grow into galaxies and stars. Temperature differences, power engines, chemical gradients nurture life. Memory accumulates in brains like ours. We remember breakfast and not dinner from tomorrow because the past was special. That is not an incantation. It's a compact way of stating a hard empirical fact about initial conditions. Black holes sit at one end of that arrow as monuments to hidden information. For a given mass and charge, nothing can hide more internal microstates than a black hole. The area of the event horizon plays the role of entropy. In any classical process, the total horizon area never decreases an echo of the second law. Let quantum fields speak, and the whole has a temperature. It can radiate faintly. These claims are not hand-waving. They rest on calculations that match laboratory physics when gravity is weak and reduce to tested predictions in regimes we can reach. The details how information is encoded and returned are frontiers, not foundations. But the headline is secure temperature, entropy and time are not bystanders in gravity, they're woven into the script. Gravitational waves tune the same idea into music. When two black holes merge, their final ringing is a pattern of space-time itself settling down, and our interferometers measure that ring down as a timed sequence of crests and troughs. The detectors are, in a sense, exquisite comparative clocks. Arms in different directions live through slightly different stretches of time and length as the wave passes, and the lasers tell us by how much. Stretch this idea outward, and you can see why space-based observatories listening at millihertz rather than kilohertz will sample the deeper bass of the universe. Slow dances of supermassive pairs, whispers from compact objects falling into giants. Each signal is a record of time carved by gravity's hand. Because you asked for images that sit comfortably in the mind, collect a few more that carry numbers as well as pictures, airliners and atoms. A typical long-haul flight flown eastward, adding to Earth's rotation speed, leaves the traveler's clock behind by tens of nanoseconds. Westward flights may let it creep ahead by a similar whisper. Atomic clock flights in the 1970s measured these effects. Modern versions show them with far cleaner precision. The sign and size match special and general relativity's predictions to the part per trillion level. The space station ledger. Astronauts on the International Space Station orbit at roughly 7.5 kilometers per second and live a few hundred kilometers higher than us. Speed slows their clocks by about 20 odd microseconds per day. Altitude speeds them by a few microseconds per day. The net is a daily loss of around 24 microseconds. Over a 6-month mission that adds up to a couple of milliseconds. Not party-worthy, but undeniably there. GPS housekeeping. Navigation satellites cruise in medium Earth orbit, where weaker gravity speeds their clocks by roughly 45 microseconds per day, while orbital motion slows them by about 7. Engineers set the onboard frequencies so that once aloft the clocks, as seen from Earth, keep perfect time. If they didn't, your phone's position would drift by kilometers each day. All of this can feel grand until you put it back into a single human scene. Picture a reunion in a railway cafe. Two friends set their watches together at the start of the day. One rides the straight local reading and daydreaming. The other dashes off on express trains, jumps trams, climbs a hill to a lookout, then races back. They meet again at twilight, clink glasses and compare dials. The numbers disagree by an amount too small for their eyes, but not for a pair of atomic clocks tucked in their bags. Neither cheated. The world kept books according to the routes they chose. Where does that leave the romantic ambition of travelling back? The equations admit curiosity's wormholes held open by negative energy densities, cosmic strings with enormous tension, tipping the cones of causality until they meet themselves. But holding a wormhole throat open at human scales appears to require exotic matter in amounts and forms we have no evidence for. Attempts to arrange such conditions grow unstable under the very quantum fields we trust everywhere else. The best summary is plain forward travel is available and measured. Backward travel remains speculative, fenced by theory, and unblessed by observation. The universe seems to value consistency over nostalgia. If you want a final exercise for the imagination, go outside on a cloudless night. Choose a star near the horizon and another overhead. The horizon star's light has been filtered through more atmosphere. It twinkles and reddens. The one overhead is crisper. Between them lies more than brightness. They are messengers with different delays. The nearby star speaks from years ago. A faint galaxy, if you can pick it out, whispers from a time when the Earth was young. You can't answer them quickly. Your reply must ride light's fixed speed and the rules of causality. Yet the conversation is real. You are embedded in time's landscape, already walking your world line, whether you notice or not, collecting seconds that are yours alone because of the route you take. A light clock on a stage gave us the first glimpse. Muons falling through the sky and satellites whispering to phones made it practical. Neutron stars and black holes made it dramatic. Gravitational waves turned it into music. And the cosmic background hummed a tempo the whole universe can approximately sensibly share. From those pieces, a clear answer emerges. You can travel into the future by moving fast or by lingering in gravity's valleys. You cannot, on present evidence, loop back into yesterday. In exchange, you get a cosmos where cause and effect are clean, where memory makes sense, and where the wonder you feel staring up is paid for in full by the honesty of the rules. Take one quiet breath and picture a simple seeing you, a small wristwatch and a sky that has just turned dark. The watch ticks with its steady pulse. The sky answers with older pulses starlight that began its journey minutes, hours and millions of years ago. Between the two is everything we've talked about: light's fixed pace, the gentle bending of time by motion and gravity, and the clean rails of causality that keep the story coherent. Nothing mystical is required to make this moment beautiful. The laws are enough. Let the day's noise fade a little. Think of time as a landscape you've learned to read. You now know where the ground slopes down into gravity's valleys, where clocks slow, and up onto high plateaus where they tick a trace faster. You know how the wind of speed leans against you when you move quickly, making your seconds stretch. You can sketch a map. Straight paths between meetings give you more personal time. Paths with turns and rushes give you less. None of it depends on opinion. All of it is written into the fabric that carries you. Hold three small pictures together like postcards in a pocket. First, the river. Close to the bank where the water idles, a leaf takes its time. Out in the faster channel, it covers the same stretch in fewer strokes. Clocks are those leaves. Each one feels honest to itself. The differences only show when they meet again and compare notes. Second, the railway. Two travellers set off, one on the straight line across the plain, the other taking switchbacks through the hills. They reunite. The dials disagree by a whisper. The route, not a hidden hand, wrote the difference. Third, the library. Shelves hold every chapter the universe will allow. The arrow you feel while reading is your brain's way of moving through a world that began remarkably simple and has been busy becoming intricate ever since. If your mind wants a fact to anchor the calm, choose one that is at once modest and profound. Lift a superb clock by the height of a step and it runs a touch faster. Set it in a basement and it runs a touch slower. The world notices. Our systems notice. Satellites are tuned so carefully to this truth that your phone can point you to a doorway. The universe is subtle, yes, but it is also practical. You live inside these rules every day. Now let your gaze go farther. Imagine a neutron star, city-sized, star-heavy, where an hour near the surface would be only part of an hour far away. Imagine a supermassive black hole horizon wide as 1,000,000 Earths, around which time thickens for any craft that dares skim close and then pulls away to return home. These are not promises to build contraptions. They are the universe telling you what is permitted and what is not. Travel into the future is permitted by speed and by gravity. Travel into yesterday is so far a whisper the equations allow, but reality keeps behind good locks. Think about how kind that consistency is. Cause leads to effect, signals obey their cones, messages take their time and not less. It lets promises mean something, it lets memory build, it gives you a sane way to plan. And within those clean rails there is room for wonder ripples, in space-time passing through us, like faint music. The afterglow of the first light bathing everything with its soft temperature. Particles born high in the atmosphere living longer than they should because motion dilates their days. The universe is honest and imaginative at once. Bring it back to ground level once more. A friend takes a long flight east, another stays home. Their clocks part by a sliver, then reunite. A pair of mountaintop observatories lives through a shade more time than the towns below. Astronauts come home younger by milliseconds. None of this is romantic exaggeration. It is the ledger of the world kept with exquisite pens. When you remember that ordinary moments gain a quiet glow. Waiting at a crosswalk, you are already a traveller with a personal tally. Your seconds counting along a path that is yours alone. If you want a simple habit to keep the map clear in your mind, try this when you step outside at night. Pick one thing near and one thing far. Near could be the moon with light a little over a second old. Far could be a faint smudge, another galaxy whose shimmer left when our species was not even a plan. Say hello to both. They are different kinds of now arriving together to meet yours. Your greeting back would take the time it must. That patience is not a burden. It is a gift, a universe where waiting has meaning because the rules are steady. And if ever the scale begins to feel overwhelming, return to the light clock on the stage. 2 mirrors, a beam of light, a heartbeat you can almost hear. Tip the clock into motion and the beat slows. Set it in a gravity well and the beat slows again. That small device contains the whole story. The same principle that guides satellites, that shapes the edges of black holes, that sings in gravitational waves, begins with that tiny, faithful bounce of light. Precision and awe are neighbours. So the ending is really a beginning. You know enough to see why your seconds are local, why paths matter, and why the world does not let you turn back a page, however tempting the thought. You know enough to spot time's fingerprints in a phone that finds your street in a star, whose heartbeat dilates with distance in the quiet arithmetic of 2 friends comparing watches after a journey. You have, in other words, a way to be at home in a universe that is larger than any single life and yet intimate in the way it keeps time with you. Walk back inside with that calm. The same laws that choreograph distant galaxies are in the room, shaping the silent tick of your watch, the red glow of a standby light, the path of a message finding its way to you. Let those laws do their work. Let the seconds arrive as they always do, one by one, yours to collect along the route you choose. And if you look up again before you turn out the last light, give the sky one more small wave. The reply will come when it can carried by the same faithful speed and the same honest geometry, and you will be here to receive it present steady and exactly where you are meant to be on the map of time.